Hey everybody, today we're going to do a little bit more with statistics versus probability. Before we do anything new, we're just going to do a quick refresher, okay? Recall that in probability, we know the makeup of the entire sample space. Remember that the sample space is the set of all possible outcomes. So in probability, we know the makeup of the entire sample space. And we try to predict the likelihood of possible events based on our knowledge of the sample space. And we use this formula. When all of the outcomes in the sample space are equally likely, we say that the probability of an event E occurring is the number of outcomes that result in E divided by the total number of outcomes. Now let's review this again. In probability, we know the makeup of the entire sample space. In statistics, this would be what we call our population. So in probability, we know the makeup of the entire population. That is the entire sample space, the set of all possible outcomes. We know that in probability. And in probability, we try to predict the likelihood of possible events based on our knowledge of the sample space. And remember what an event is? An event is a subset of the sample space. So an event is a subset of the sample space that contains 0 or more outcomes in the sample space. An event could actually be a subset that contains 0 outcomes. And the probability of that event occurring would just be number of outcomes resulting in E, which would be 0, over total number of outcomes. So an event could be a subset that contains 0 outcomes in the sample space. And that would just mean the probability of that event occurring is 0. But let's get the main characters down pat, because we want to make a comparison between probability and statistics. In probability, we know the makeup of the entire sample space. That is the set of all possible outcomes. In statistics, we would call this set of all possible outcomes the population. Now, given that information, given our complete knowledge of the entire sample space or the population, in probability, we try to predict the likelihood that an event will occur. And the probability that that event will occur is number of outcomes that result in that event divided by the total number of outcomes, or the total number of outcomes in the population or sample space. Now, let's look at what statistics is. Okay, now we talk about statistics, probability in reverse. In statistics, we don't have complete knowledge of the entire sample space, which we call the population. In statistics, we don't have complete knowledge of the entire population, of the entire sample space. We try to make an accurate inference about the makeup of the entire sample space or population based on the results of an experiment. So essentially, the experiment is going to be a survey of random randomly selected people and we look at the percentage of people in the survey that do this or the percentage of people in the survey that like that. In statistics, we don't have complete knowledge of the entire sample space or the entire population, which is the set of all outcomes. We try to make an accurate inference about the makeup of the entire sample space based on the results of an experiment. By the way, if we are doing statistics and we do an experiment, exactly what is the population? Well, suppose that we were trying to figure out the percentage of American men that do such and such. The entire sample space would be the entire population of American men in this country. You know, all 150 or 60 million of them. Now statistics gets a chance to be in the limelight. In statistics, we try to make an accurate inference about the makeup of the entire sample space or population. And we do this based on the results of an experiment. What kind of experiment? We don't know yet. We'll find out. But in statistics, we try to make an accurate inference about the makeup of the entire sample space or the entire population based on the results of an experiment. Okay, the experiment could be a survey of randomly selected people, something like that. The individual values obtained in the experiment are called data. Each individual value is called data. All of the individual values grouped together are called data. If you have one piece of information, it's data. If you have a million pieces of information, we call those million pieces data. So the individual values obtained from the experiment are called data. The data can be grouped into disjoint categories called classes. If we do a survey of 10,000 people, we don't want to look at 10,000 different outcomes. We want to group those 10,000 different outcomes into anywhere from 5 to 10 to 15 different disjoint classes that will give us some insight as to the composition of the entire population. So the data that we get from our experiment is grouped into disjoint categories called classes. These classes are disjoint, which means that no piece of data winds up in more than one class. And we'll find out that every piece of data winds up in some class. So we could say that every piece of data ends up in exactly one class. When we group this data into classes, we form a frequency distribution. So the set of classes is called the frequency distribution. Now, should all of this be crystal clear? No, absolutely not. And that's why in math we have examples, and we're going to look at a few. Here's a good example. 1,000 American women are selected at random from a recent census. The women were grouped according to age into 11 classes. The number of women in each class is listed below. 0 to 9, this is a class. 10 to 19, this is a class. 20 to 29, this is a class, and so forth and so on. They don't overlap. And just so that we don't have any misgivings as to what these classes really are, 0 to 9, so that would be 0, the time they're born, until one day before their 10th birthday. One day before their 10th birthday, they're still considered to be 9 years old. 10 to 19, this is all the women whose birthday these are all the women who had their 10th birthday or were at least one day shy of their 20th birthday. Okay. These were women who had observed their 20th birthday but were at least one day shy of observing their 30th birthday, and so on and so forth. So every one of these 1,000 women appeared in exactly one of these classes. And we call this a frequency distribution because it records the number of times that women from this group appeared in a particular class. Women appeared in the 0 to 9 class with a frequency of 115 out of 1,000. Women appeared in the 10 through 19 class and a frequency of 122 per 1,000. Women in the 20 to 29 class appeared in this 20 to 29 class with a frequency of 31 out of 1,000, so on. And let's see, what else can we say about this example? Give me a minute, I need time to think. Let's make some observations about this thing. Oh, by the way, I don't know if I mentioned it before the pause, but if I didn't, I should. This is a frequency distribution. Of the ages of women sampled. So this entire table is a frequency distribution of the ages of the women sampled. Another way that we can say this entire table is a frequency distribution of the data. So this is what a frequency distribution might look like. Note some other things. All classes have the same width, 10 years. And we might see this and say, wait a minute. No, it'd be 9 years. Well, let's see. Let's look at the first class, okay? And in the first class, women in that class can be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 years old. How many different ages are there in that class? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can do the same thing with the 10 to 19 class and the 20 to 29 class. all of these classes have the same width, 10 years. And this is always characteristic of a frequency distribution. Note too that the classes are disjoint. This is, in other words, no data value goes into more than one class. In fact, every piece of data, that is the age of every woman surveyed, appears in exactly one class. So every piece of data goes in exactly one class. No piece of data gets left out of a class. No piece of data appears in more than one class. And that's reflected by the fact that if we add up the numbers of data in each class, in this case, if we add up the number of women in each class, all of this is going to add up to 1,000, the number of women that were sampled. Or we could say all of these pieces of data are going to add up to 1,000, the total number of pieces of data. And this is always the case in a frequency distribution. In a frequency distribution, the classes all have the same width. In a frequency distribution, the classes are disjoint. No piece of data winds up in more than one class. And in every frequency distribution, every piece of data winds up in a class somewhere. Every piece of data winds up in exactly one class. This is always the case with a frequency distribution. Just for emphasis, in a frequency distribution, all classes have the same width. Maybe I should underline that. In a frequency distribution, all classes have the same width. All classes are disjoint, so no piece of data belongs in two or more classes. There's no overlapping. No piece of data belongs to more than one class. And in a frequency distribution, every piece of data belongs to exactly one class. So nobody gets left out. Now we'll do an example where we take the raw data and take that data from an experiment and create frequency classes. This is a good example. Pat Rossi is unacquainted with games of chance and has no idea how to compute the probabilities of each event when tossing a pair of dice. What's the probability of getting a 7 when he tosses a pair of dice? He doesn't know. So he tosses a pair of dice 36 times and records the results. He intends to use the data to construct a frequency distribution. And here are the different outcomes that he gets when he tosses that pair of dice 36 times. 36 different numbers, all between 2 and 12. This is what he got when he tossed the pair of dice 36 times. Now he's going to make a frequency distribution. What do you think the classes of the frequency distribution should be? Remember, Pat Rossi has no idea how to compute the probabilities of each event when tossing a pair of dice. Well, when we toss a pair of dice, what are we really interested in? It's the sum of the two dice, right? And the sum of the numbers on the two dice can be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So perhaps each of those numbers should have their own class. We'll make 2 the class of all outcomes that resulted in a 2. We'll have 3 be the class of all data values that resulted in 3. We'll have the class 4 be the class of all data values that resulted in 4, and so forth. That's what we're going to do. Okay, let's record how many times each distinct data value appears and record. Let's look for 2s first, okay? Here's one. Let's see, 2, 2, 2, 2, 2, 2, 2. Is that the only one? Yikes. 2. I think so. Okay. 2 appears once. And we'll remove this from the list so that we don't record it again. Let's look for 3s. Here's a 3. And here's a 3. Are those the only 2 3s that we have? It looks like it. Okay. And we'll take these 3s and eliminate them from the list so that we don't make the mistake of counting them again. 4. Here's a 4. Here's a 4. Here's another 4. And here's another 4. How many are there? 1, 2, 3, 4 4s. Okay. And I'll erase those so that we don't somehow count them again. And also I'll erase them so that the remaining numbers will be easier for us to pick out. We're up to 5 now. Here's 1. 5, 5, 5. Here's another one. And another one. Son of a gun. Only 3 5s. Well, I guess. Yeah, I guess so. Okay. 3 5s. And as we erase these, we'll keep our eyes open for any that I might have missed. Okay, now on with the 6s. 6, 6, 6, 6, 6. Here's 1, here's 2, here's 3, here's 4, 5, 6. Did I get them all? I think I did. 1, 2, 3, 4, 5, 6. Okay. And I'll get rid of my 6s so that the rest of the numbers will stand out and be easier to record. Here's one I missed. Okay. On with the 7s. Here's 1, Okay. Next on the agenda, 8. Here's 1, 2, 3, 4, 5. We got 5 8s. I guess 9 is up next. And here's a 9, another 9, a third 9, and a fourth 9. So we have 4 9s. Okay. What's up next? 10, 10, 10. 2 10s. Okay. 11s, 3 11s. Zip, zip, zip. 3 11s. And 12s, we have 1 12. Oops. And let me just check and make sure that I didn't mess up. Although if I did, it might be hard to correct my work because I erased all of the data. Okay. But here's what I should check. I should check that the number of data recorded in my frequency distribution adds up to the total number of data. Remember, I tossed the dice 36 times and I recorded the results. So I should have 36 data values here. So let's see. 1 plus 2 is 3, plus 4 is 7, plus 3 is 10, plus 6 is 16, plus 5 is 21, plus 5 is 26, plus 4 is 30, plus 2 is 32, plus 3 is 35, plus 1 is 36. Okay, it appears that I did not goof up. All of the data values are here. And this entire table, is my frequency distribution. And just for emphasis, what about my classes? The value of 2 is a class. The data value of 3 is a class. The data value of 4 is a class. The data value of 10 is a class, as are 5, 6, 7, 8, 9. The data value of 11 is a class, and the data value of 12 is a class. So my classes are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And notice, by the way, that we constructed this frequency distribution that every data value, every roll of the dice, wound up in exactly one of these classes. Notice that the classes are not overlapping. 2 and 3 don't overlap, 3 and 4 don't overlap, and so forth. The classes are all the same size, 1 unit. The width of each class is 1 unit. And every value that I got when I rolled the dice appeared in exactly one of these classes somewhere. No value that I got was left out. Here's an example of the likes of which we'll probably see in the homework. And it says, use the data below to create a frequency distribution whose first class or whose lowest class is 12.0 to 15.9. So I guess the first thing that we need to do is figure out what all of our classes are. And remember some principles of classes of frequency distributions. They all have to be the same width. What's the width of this thing? It turns out the width is 6. It goes from 12.0 to 12.9, 13.0 to 13.9, 14.0. Let me write that down. This class goes from 12.0 to 12.9 and 13.0 to 13.9, 14.0 to 14.9. That's not what I want to do. Hold on a second. Let me rewrite this because I'm going to have 12 classes. That's a bit too much. We'll go with this. I said the width was 6. I must have been out of my mind. The width is 4. 12.0 to 15.9. to 15.9. This has a width of 4. It goes from 12 up to, but not including 16. 12 to 15.9. Each of these classes has 10 there are 10 data values that can go in each of these classes. 12.1, 12.2, dot, dot, dot. I'm sorry. 12.0, 12.1, 12.2, dot, 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 12.9. That's 10 data values here, 10 data values here, and so forth. They're all of the same width. They go from something 0.0 to that same thing 0.9. This has a width of 1, this has a width of 1, this has a width of 1, this has a width of 1. So the width is 4. So based on this, let's see how many classes we have to have to include even the highest data value. We have one class, 12.0 to 15.9. That's one class. Our next class is going to start where this one left off at 16.0. And it's going to go to, let's see, 15 is 3 greater than 12, 19 is 3 greater than 16. This is actually 4 units. 16 to 16.9, 17 to 17.9, that's 2. 18 to 18.9, that's 3. 19 to 19.9, that's 4. The next will start at 20.0 and go to 23.9. Again, this has a width of 4 because it goes from 20.0 all the way up to, but not including 24. The next one will start at 24.0 and go up to, but not including 28. So it will stop at 27.9. And the next one will start where this one leaves off, 28.0. And it will go 4 units. It will go up to, but not including 32.0. So this will go to 20, no, this will go to, what's right before 32.0? 31.9, okay. And this one will be 4 units wide, so it will go up to, but not including 36.0, so this will stop at 35.9. And this one will go up to, but not including 40, so it will stop at 39.9. And this category, this class, will accommodate our highest data value. Now, I did that rather clumsily, so let me go over my logic again, now that I've figured it out. Every class has the same width, 4. The first class, we want to be 12.0 to 15.9. Why? Because that's what we were told in the instructions. Our first class would go from 12.0 to 15.9. So another way of looking at this is that our class starts at 12.0 and it goes up to, but not including 16.0. It stops right before 16.0, and that puts us at 15.9. This class starts at 16.0, and it has a width of 4. So it will go 4 units more and stop at 20.0. It will stop at 20.0, but not include 20.0. So we'll go up to, but not including 20.0, which means that it will stop at 19.9. It includes 19.9. Starting at 20.0, we go 4 units to 24.0, but not including 24.0. So this class will end at 23.9. At 24.0, if we go forward 4 units, we go to, but not including 28.0. But we'll include everything up to 28.0. So starting at 24, we'll go 4 units up to, but not including 28.0. So this will stop at 27.9. Starting at 28.0, we'll go 4 units up to, but not including 32.0. We'll stop at 31.9. At 32.0, we'll go up 4 units to 36.0, but not including 36.0. It'll stop at 35.9. 36.0 will go up to, but not including 40.0. So we'll stop at 39.9. Now let's put this in a nutshell, hopefully a bit tidier than what I just did. 12.0 going up to, but not including 16.0. 12.0 going 4 units up to, but not including 16.0. 16.0 going 4 units up to, but not including 20.0. 20.0 going 4 units up to, but not including 24.0. 24.0 going 4 units up to, but not including 28.0. 28.0 going up to, but not including 32.0. 32.0 going up to, but not including 36.0. These are our classes. Now, they've done us a favor here by listing all of this data from highest to lowest in order. So the first class goes from 12.0 to 15.9. This is the first data value going upward that's not less than 15 point, or not less than 16.0. All of these other values are between 12.0 and 15.9. And how many do we have? 1, 2, 3, 4, 5, 6, 7, 8. Okay. 8 values here. And we'll erase these guys. Now the data values between 16.0 and 19.9, including 19.9, there are 4 of them. We record the number of data values. The next set between 20 and 23.9, wow, that's all of these. And we have 6 of those, okay. And we'll get rid of all of these. (24 to 27.9). This one fits the description. We have one value between 24 and 27.9. We'll erase this. 28 to 31.9, we don't have any. We'll put a big fat 0 here. 32 to 35.9, nope. We'll put another 0 here. And 38.0, yes, that does go in our last class. So we will put a 1 here. And this is our frequency distribution having the characteristic whose first or lowest class is 12.0 to 15.9. And I have one more thing to talk about. It's a leaf diagram. Okay, we're going to do stem and leaf displays. A stem and leaf display is a method of displaying data having 2 or more digits. The rightmost digit or digits form the leaf. The remaining digit or digits form the stem. Here's a case where, according to a predetermined criterion, the leaf is going to consist of the rightmost digit only, 1 digit, and the remaining digits, the 2 and 8, form the stem. We'll look at the same number, 287. This time, our predetermined criterion specifies that the leaf will have 2 digits, and the remaining digit or digits form the stem. Here, the leaf consists of the 2 rightmost digits, and the remainder of the digits form the stem. The data is displayed vertically in ascending order, with the stems and leaves separated by a vertical line. Make sense? Probably not. Let's do an example. Here's our example. 10 commuters are surveyed regarding the number of miles round trip that they commute to and from school. These, well, let's see, are the results. 12 miles, 18 miles, 6 miles, 42 miles, 14, 58, 16, 38, 15, 60. Construct a stem and leaf diagram. Stem and leaf are each 1 digit. So the rightmost digit will be the leaf, the leftmost digit will be the stem. And the first thing I'm going to do is I'm going to arrange these numbers in ascending order. And let's see, we have 6. That appears to be the smallest. 12, 14, okay, 12, 14, 15, 16. And let me scratch those out so that I don't write them down again. And 18, okay. None in the 20s, huh? How about that? We got the bottom 6. What's next? 38 and then 42. And then 58 and 60, and that should exhaust everything. Now here's how we're going to do it. For a number like 12, the 2 is the rightmost digit, that's going to be the leaf. And the 1 is the leftmost digit, that's going to be the stem. The data is arranged vertically, like we have it, with the leaves on one side of a vertical line and the stems on the other. And do you see a problem here? This is a single digit number. Oh my goodness, what am I going to do about that? No problem. We'll just put a 0 here. And the 0 will be the stem. The 6 will be the leaf. What's the smallest stem? It's 0, right? So we'll put 0 here, and we'll put its leaf over here on the right. The next smallest stem is 1, and holy moly, we got 5 of those. But we're just going to have one stem, but we have 5 leaves, 2, 4, 5, 6, 8, and we're going to put them like this. And then we have a stem of 3 with 1 leaf, 8. We have a stem of 4 with 1 leaf, 2. We have a stem of 5 with 1 leaf, 8. We have a stem of 6 with 1 leaf, 0. And I think that's the way I like it. Let me take a quick look. Yep, I think this is exactly what I want. So let me encapsulate that with a marker. Here's our stem and leaf diagram. Just a couple of reminders. Here we had a 1-digit number, the rest were 2 digits. So we just put a 0 out in front for the stem. That's what we do when one of our data has 1 fewer digits than the rest of them. We put a 0 to the left to form the stem. Something else, for each stem, 0, 1, 3, 4, 5, 6, we only have 1 row. We only have 1 row for each stem. And next to the stem, we'll put all of the leaves in ascending order. We had 5 stems equal to 1. We put a 1 here in the stems column, and then we put the leaves, 2, 4, 5, 6, 8, in ascending order in the leaves column. Everybody, I think that's a wrap.